Hey everyone, and welcome to my lecture on filtering for periodic signals. This topic is very sweet and easy to learn. As the name shows, the whole idea behind filtering is to pass some stuff and reject the rest. As we learned in the last lecture, when a complex exponential function with the frequency of omega naught goes through an LTI system, the output is basically the same function multiplied by h, or frequency response, at the frequency of omega naught. Also, we learned that hj omega naught, or in general hj omega, is equal to this integral. In the previous lecture, the integral variable was tau, not t, but it doesn't really matter. The variable is just a name. You can call it whatever you want. Also, some people call the frequency response h of omega, not h of j omega, to be consistent with the notation used in the famous signal processing books. I go with h of j omega. Hj omega is called frequency response, and it basically means how system responds to different frequencies applied to the system. Before I continue, let me just quickly mention one thing. As we will learn in the next tutorials, this integral is the Fourier transform of ht, which is the impulse response for this LTI system. Again, this integral is the definition of Fourier transform. But don't worry about it for now. The main focus for this lecture is the frequency response. Let me emphasize again, frequency response means how system treats different frequencies. For example, if we have this frequency response, all the frequencies in this range will be rejected by the system as h is 0, and all the frequencies in this range will be passed as h is 1. This system is called low-pass filter, as it lets low frequencies pass. Here's another example of frequency response which passes all the frequencies in this range and rejects the frequency here. This system is called high-pass filter, as it just allows high frequencies to pass. Here is the next example of frequency response that rejects high and low frequencies and passes the frequencies in the mid-range. This is commonly referred to as a bandpass filter. As you can guess, there is also a bandstop filter which passes high and low frequencies and rejects the frequencies in between. To help you understand the concept of filtering better, I'm going to show you two simple applications of low-pass and high-pass filters in image processing. I will show you some cool applications of bandpass and bandstop filters in the future. Let's say we have an image of this handsome guy, who is by the way me. And let's say the image somehow gets extremely corrupted by noise. This noise is called salt and pepper noise in image processing, as it's like we scatter lots of salt, i.e. white points, and pepper, i.e. black points, over the image. As I explained in the frequency concept lecture, frequency means how fast a signal is changing. So we can conclude that the salt and pepper noise is a very high frequency signal, as it's changing so fast. In fact, we go from pure white to pure black and vice versa in a very small area. Now, to get rid of noise, I'm going to apply a low-pass filter to the image. As you can see, the high frequency noise is almost gone. This is one application of low-pass filters in image processing. Now I'm going to show you a simple application of high-pass filters in edge detection. Think about it. What is an edge in the image? An edge is basically an area where we have fast changes, i.e. high frequencies. For instance, as we move from the ocean in the background to my jacket, we are moving from almost white to black color. So there should be an edge around me. Now I'm going to apply a high-pass filter to the image to detect the edges. Again, edges are high-frequency signals. Here's what I get. As you can see, almost all edges have been detected. I will show you some other applications of filtering in the future. Okay, let's continue with the mathematical explanation of filtering. As was already mentioned, when a complex exponential function with the frequency of omega naught goes through an LTI system, the output is the same multiplied by the frequency response at omega naught. As we learned in the previous lecture, an LTI system does not change the frequency. So, if the input frequency is k omega naught, the output frequency is k omega naught multiplied by the frequency response at k omega naught. Also, as we saw in the system properties lecture, for a linear system, if we multiply the input by ck, the output is multiplied by the same value. Again, because the system is linear, a linear combination of inputs results in a linear combination of outputs. What does this mean? If we can represent a periodic signal, let's say xt, as a linear combination of complex exponentials and apply it to an LTI system, in the output we have the same complex exponentials multiplied by the frequency response at each specific frequency. This is very, very useful. Why? Because it helps us to find the output without doing time-consuming convolution between xt and ht. Instead, using Fourier series, we just need to multiply each exponential function by the frequency response. So instead of convolution, we have bunch of multiplications. This simple thing forms the foundation of filtering. For instance, if we want to pass a specific frequency, we just need to set the frequency response at that frequency to 1. Or if we want to reject a specific frequency, we should set the frequency response to 0. The first step to do filtering in the frequency domain is to represent a periodic signal in this form. As I explained in the previous tutorial, you can think of different frequencies k omega naught as different colors, and ck are the weights for each color. In general, to find ck or the weights, we need to find this integral. However, if the signal is just a bunch of sinusoidal or cosine functions, there is a simpler way to find ck. In this case, Mr. Euler can help you represent sine and cosine in terms of complex exponentials. Just to refresh your memory, as we learned in the complex number lecture, sine A can be expressed in this form, and here's the cosine. We already practiced how to find ck using this integral in the previous tutorial. In the next example, we're gonna practice finding ck using Euler. Example: this signal is applied to an LTI system, and the question is, what is the output if A, the frequency response, is like this, which is basically a low-pass filter. B, the frequency response is this, which is a bandpass filter. C, the frequency response is this, which is a high-pass filter. Before I solve this example, I want to make something clear. The threshold to decide if a frequency is low, or medium, or high is relative, not absolute. For example, in one application, 5 can be a high frequency, and in another application can be a low frequency. So it's all relative. Okay, let's continue. The first step in filtering is to represent the input as a linear combination of complex exponentials. Here, the input signal is a bunch of cosine functions. So we can use Euler to present cosine function in terms of complex exponentials. So we get 1 plus 2 multiplied by cosine 2t is replaced by this, plus 2 multiplied by cosine 4t is replaced by this. 2 is cancelled by 2, the same thing here. Also, to present 1 in this form, I'm going to replace it with e to the power of j0t. It's basically the same thing. E to the power of 0 is 1, and here's the rest. So we just represented xt as a linear combination of exponential functions. Now the question is, if we apply these signals to the LTI system, what is the output? As we learned, when a complex exponential function with the frequency of omega naught goes through an LTI system, the output is the same, just multiplied by the frequency response at that frequency. So, if this is the input, the output is the same, just we need to multiply each complex function by the frequency response at that specific frequency. Here we go. Now let's start with the first case. H at 0 is 1, so the system passes this signal. H at 2 is 0, so the system rejects this signal. The same thing for minus 2. H at 4 is 0, therefore this signal is rejected. The same thing for minus 4. So this guy is the only signal which is passed by the system. So the output is e to the power of j0t, which is 1. Let's consider the second case. First, let me erase these lines. In this case, h at 0 is 0, so the system rejects this signal. H at 2 is 1, therefore the system lets this signal pass. The same thing for minus 2. H at 4 is 0, so the system rejects this signal. The same thing for minus 4. So these guys are the only signals which are passed by the system. So the output is this. Let's look at the remark again. This value is basically A, but 2 is missing at the bottom. So let's divide the whole thing by 2 and multiply it by 2. Look, it's the same thing. 2 can be cancelled by 2. Now you can write this one as cosine 2t. Here's the final answer. Finally, let's consider this frequency response. Again, I'm going to clean these lines. In this case, h at 0 is 0, so the system rejects this signal. H at 2 and minus 2 is 0, so the system rejects both signals. H at 4 and minus 4 is 1, so the system lets this signal pass. Here's the output. Similar to the previous case, you can divide this by 2, multiply it by 2, and write the expression inside the parentheses as cosine 4t. That's it. Let's just step back for a moment and try to understand what these calculations mean. The input signal in this example is this. 1 is constant and its frequency is 0 as it's not changing. Cosine 2t is something like this. And cosine 4t is like this, 2 times faster than cosine 2t. We can consider this as the low frequency signal, this as the medium range frequency component, and finally this signal as the high frequency component. Now let's look at the solutions again. If we consider this frequency response, which is a low pass filter, the system just passes the low frequency component. If we consider this system, which is bandpass, the system passes the medium frequency signal and rejects the others. Finally, if we consider this case, which is a high pass system, just the high frequency component can pass. So that was the meaning of filtering. I will talk about this topic again when I'm covering Fourier transform. Okay, that's all I want to say for this tutorial. If this video was useful, please like it, and if something was not clear, write your question in the comments section. To make sure that you are not missing the upcoming tutorials, please subscribe to my channel. Thanks again for watching this tutorial and see you in the next video.